Hey everyone, this is going to be a video summary of Lewis dot structures, which there are a number of ways to approach these, and if you've learned a different way in the past, that's fine. Um, and as long as you're getting consistent results and that are consistent with my results, the exact method you do is not at issue. But I'm going to go over in this video what I think is the most systematic way to do it. So just briefly, Lewis structures are, or Lewis dot structures or Lewis dot diagrams, you see them called a lot of things. It's basically a method for predicting stable structures of molecules. This was, in other words, what if you could zoom in on a molecule at the atomic level, what atoms are bonded to which ones? It's actually a remarkable model because it was created before our modern understanding of even how electrons behaved. In atoms, all the electron configuration stuff that we've learned was figured out in the 1920s, 30s, 40s. This model actually dates from the early 1900s. This was by a chemistry professor at UC Berkeley named G.N. Lewis, who I worked in the building named for him when I was in graduate school. So anyway, this is a cool way to predict structures, but it's just a model. So there's, you should not take anything in here as like this is somehow explaining how atoms behave, but it is a model that works pretty well with the data that we get once we get into later, decades after this. A lot of these structures were proven correct. And so it's a really useful model for you to have in your toolkit. All right, so the best way to do this is just to do some examples. So we're going to start with carbon dioxide. The way you do this is that the only electrons that matter are valence electrons, right? The core electrons don't participate in bonding. So the valence electrons are all that's going to matter, and we're going to add those all up first. So if you think about carbon, its electron configuration is 1s2, 2s2, 2p2. So these are your valence electrons. So it's got 4 valence electrons. Oxygen, so that was carbon. Oxygen is 1s2, 2s2, 2p4. So the 2s and the 2p electrons are valence, so there's 6 for oxygen, right? There's a shortcut for this, and I'll show it to you in a minute. So anyway, the carbon has 4. Each of the 2 oxygens contributes 6 valence electrons to the molecule. So that's going to be a total of 16 valence electrons. So now we're going to draw, so that's the first step, is count valence electrons. Okay, so step 1, count your valence electrons, not your valence electrons, the valence electrons for the molecule. All right, so now we're going to draw just a simple structure where we are just holding the atoms together. Okay, so draw a simple structure. Some people call this a skeleton structure, whatever you want to call it, it's good. And in this structure, we've drawn these lines without any explanation. The lines that we're drawing here are going to represent covalent bonds. And covalent bonds are shared pairs of electrons. Okay, and the theory for this I'm not covering in this video because we're just doing nuts and bolts of how to draw the structures. But there are good reasons why we think of shared pairs of electrons as a covalent bond. And again, I'm not getting into that. So some folks prefer to represent the bonds as pairs, like literal pairs of electrons, like writing it like this, and that's fine. If you prefer that, you're more than welcome to do that. I'm going to use lines for bonds because that's kind of how we tend to use these later on. Anyway, so you need to think of each of these lines here as a pair of electrons. So there's 2 electrons in this bond, there's 2 electrons in this bond. So out of our 16 that we had to begin with, we've used up 4 electrons, okay? 2 electrons in each of 2 pairs. So we have 12 electrons left to distribute around the molecule. So we're going to erase these arrows here because they're going to get distracting. And we're going to take our 12 electrons and we're going to distribute them more or less evenly around the molecule. So 2, 4, 6, 8, 10, and 12, right? So step 3, let's say we're going to subtract electrons used in step 2, and then we're going to distribute evenly remaining electrons. All right. So now in step 4, we're going to do something called the octet rule. The octet rule states that in a stable molecule, the atoms will all have 8 electrons around them. Those electrons can be bonding, so they can be in the bonds, or they can be these electrons that just belong to one atom that we call lone pairs of electrons. Either one counts towards the 8. All right. So if we look at this oxygen here, we have 2, 4 for the unbonded, the lone pairs, and then another 2 for this bond. So there are 6 electrons around that oxygen, 6 valence electrons. The carbon in the middle has 2, 4, 6, 8. So 2, 4 for the bonding electrons and 4 for the unpaired lone pair electrons. This oxygen has 6. The octet rule says that in a stable molecule, that all of the atoms will have 8 electrons around them. There is no why here. It is simply, that's the observation, all right? So don't try to take that and use it in other places where it doesn't belong, as tends to happen. It's just a rule for Lewis dot structures, all right? So the way we're going to get everything up to octet rule, to meet the octet rule, is the carbon is the only one here that has 8. So what we're going to do is we're going to take 2 electrons that are unpaired from the carbon. We're going to erase those, and we're going to move them into a second bond with the oxygen on the right. Now this oxygen has 8 electrons around it, and it now satisfies the octet rule. The oxygen on the left-hand side, we're going to take our eraser, we're going to erase these 2 electrons that are unshared for the carbon. We're going to move them in here to create a second bond. There are 2 bonds there. There we go. Let's try to make this neat. Okay, so now there's a second bond there. Now this oxygen also has 8 electrons, and now we've satisfied the octet rule. Okay, so step 4 is the octet rule must be satisfied. If not, we're going to make double bonds or even triple bonds if necessary, and that'll come up later. One thing here, there are some exceptions. There's some exceptions. There are a lot of exceptions to the octet rule. Hydrogen is an exception. Hydrogen is a hard exception. Hydrogen only needs 2 electrons around it. Boron can have only 6. Beryllium sometimes makes molecules with only 4. Sulfur, phosphorus, chlorine, iodine, they can actually have more than 8, which is something we'll deal with at a later point. So there's a lot of exceptions to the octet rule. It's just a rule of thumb. It usually works for atoms. It hard applies for things in that second row of the P blocks, or the first row of the P block, I guess. So carbon, nitrogen, oxygen, fluorine. It hard applies for them. Everything else, it's kind of negotiable. So, but since that's what most of the molecules in the world are made out of, it's a useful rule to have. Okay. All right. So now we're going to do this next one, carbonate. So we're just going to follow the rules. So step 1, count the valence electrons. There is a handy little trick here, which is that if you count the main group columns, which in other words, not the D block metals, you can just count the columns. So if it's in the first column of the periodic, this is a periodic table. Sorry, I don't know how you would have known that. In that first column, there's 1 valence electron, 2, there's 3 in the boron column, 4 in the carbon column, 5 in the nitrogen column, 6 in the oxygen column, 7 in the fluorine column, and 8 in that last column for the noble gases. Okay, so dig out your periodic table, stare at that for a second, convince yourself that that's the number of those taller main group columns that correspond to how many valence electrons there are. Okay, so we have 4 for carbon, 3 times 6 for oxygen. This -2 charge here means that we have 2 bonus valence electrons, so that because remember electrons are negative, so if it's a -2 charge, it's got 2 extra electrons. They have to be valence electrons, they can't be core, right? You can't somehow cram extra electrons into the core. So all together here, you've got 18, 24 electrons, all right? So we're going to draw a simple structure that holds them all together. That's going to be 24 minus 6, because each bond represents 2 electrons. All right, so that's going to be 18 electrons to distribute. So now we're going to do 2, 4, 6, 8, 10, 12, 14, 16, 18, and we're done. This oxygen and the carbon all satisfy the octet rule because they all have 8 electrons around them. Remember, it doesn't matter if they're bonded or lone pairs, either counts. This oxygen here only has 6, so we're going to take these 2 electrons from carbon and make a double bond. All right? And now it reaches 8. And now I'm going to erase these ones that I scribbled. Okay? All right, and that's going to be the Lewis dot structure for carbonate. Notice that in the subsequent video for this, we talk about what the shapes are. I'm not trying to draw them right now to reflect the accurate shape. I'm just trying to get through drawing the structures. Right. One more example, H2CO. I like this one because you might think it's going to be like this, but you can't do that because now this hydrogen here has 2 electrons there and 2 electrons there, and it's got 4. Hydrogen can only have 2 electrons around it, so this structure can't be right. All right, so let's get rid of that. That just looks crazy. All right, so what we're going to do instead is put the carbon in the middle and try it like that. All right, that structure only has 2 electrons around each of the hydrogens, so far so good. All right, so let's count valence electrons. Hydrogen has 1, carbon has 4, oxygen has 6. Oops, there's 2 of these hydrogens. So that's going to be 12 valence electrons. We've used 6 of them just to hold the molecule together, so there's 6 left over. So 2, 4, and 6. And that oxygen on the right-hand side there, or the only oxygen, is not meeting octet rule. It's only got 6. So we're going to take these 2 from carbon, and we're going to bring them in here to make a double bond. All right, so that's going to be the structure for, what is this, formaldehyde. Okay, all right. I've got some practice problems as usual, so go ahead and pause your video, get out a periodic table and some pencil and paper, and try to do these on your own, and then restart the video and I'll go through the answers. Okay, so here we go. Nitrogen is going to be 2 times 5 for the valence electrons, so that's 10. We need 2 to hold the molecule together, that's 8. So we do 2, 4, 6, 8. Both nitrogens, notice, have only 6 electrons around them. So we're going to take, here, let's scribble first. Scribble out. Now the left-hand side one meets the octet rule, but not the right-hand side, so scribble these and bring those in. Neaten it up with our eraser. Triple bond between the nitrogens, okay? It doesn't really matter where you draw the lone pairs. Some people kind of freak out about this. I am not one of those people. It's just a model, folks. You can draw it like that, wherever you want to put them. Okay, for O3, you've got 3 times 6, that's 18. So we're going to use up 4 of those to hold the molecule together. So we got 14 electrons, 2, 4, 6, 8, 10, 12, and 14. So this electron meets octet, this oxygen meets octet, the middle oxygen meets octet, this one on the right-hand side does not. So take 2 of these and make a double bond. Okay, that is ozone. All right, ammonia and H3 here, you've got, yes, I know, nitrogen, hydrogen, hydrogen, hydrogen. You've got 5 for nitrogen, 3 times 1 for each of the hydrogens, that's 8. We use up 6 holding the molecule together. So we've got 2 electrons. The only place to put them is on the nitrogen because the hydrogens, again, only need 2 electrons. They can't take any more. Okay? And then nitrate, NO3 minus. It can look like this. We've got 5 for nitrogen, 3 times 6 for oxygen, plus the bonus electron for the -1 charge. Don't forget that. 18, 24 minus 6 that we use to hold it together. So 18 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. Everyone reaches the octet rule except for the right hand oxygen. So we're going to scribble these and bring that in here. All right, there you go. One thing to notice here is I have managed to go through this entire video without saying that 8 electrons makes an atom happy. Remember, atoms don't have emotions. They are a collection of protons, neutrons, and electrons. The octet rule just has to be satisfied. It is not some kind of octet law. It is an observation only that atoms that meet the octet rule are generally, if you can draw a structure for which the atoms all satisfy the octet rule, that is usually the stable structure. There are some exceptions to that that require an additional rule that we'll learn later on called formal charge. But the point is that that we're just drawing models and we're obeying the rules and we're trusting that the rules are going to lead to structures that are going to match our experimental data for molecules. Okay? Any questions, comments, concerns, whatever you got, feel free to leave a comment or you can just get in touch. All right. Thanks, everyone.